Hey Team Bio, welcome back from winter break to your first screencast following the holidays. And this screencast is going to be about energy coordinate diagrams, and it's going to be our introduction to talking about the third class of organic compounds, the third of the big four, which is proteins. Now, proteins, remember, are made up of amino acids. They're the monomer. And when you take a bunch of amino acids and you string them together and you fold them, well, if you take a bunch of amino acids, you put them together, you get a polypeptide. And when you fold that polypeptide, you get a protein. So the shape, the folding pattern of a polypeptide is integral to creating a functional protein. So the sequence of amino acids is important, and then how those are folded is going to create our three-dimensional protein shape. And proteins have a lot of diverse functions in our body. We've talked about some of them as being structural as well as hormonal, so signaling through the bloodstream. So for example, insulin is an example of a hormone that's a protein hormone that is helping control your blood sugar level. But the function of protein that we're going to focus on over the next couple weeks is the enzymatic function of proteins. So proteins, a big class of proteins, are enzymes. And an enzyme is a biological catalyst. And what that means is that any sort of catalyst, but a biological catalyst is going to be an organic catalyst, so has a backbone of carbon. And a catalyst is something that speeds up the rate of a reaction. Oops. By lowering the energy of activation, or activation energy. Now that might seem a little bit nebulous, and I'm going to define that more later on. So this idea of activation energy is the energy necessary to get a reaction started. And a biological catalyst is going to speed up the rate at which the reaction can take place by lowering it. And an important feature of enzymes is that they're not consumed in the process of catalyzing their reactions. So an enzyme or a biological catalyst, so an enzyme, can catalyze its reaction again and again and again and again, and it's not used up when it catalyzes reaction. It's still there. So if you provide it more substrate or more reactant, it will continue to make more product. And this is all of this functionality described here is actually linked to this idea of folding or shape of the enzyme. The specific folding pattern or three-dimensional shape it takes on to create the protein is actually what gives it this characteristic of a biological catalyst. So if we change the shape, then we change its function. It will no longer work to catalyze its set of reactions. Okay, so this is a little bit nebulous, but we're going to drill down more into what this means exactly and how it plays out on a molecular level over the next few days. Okay, but now taking a step back in order to take a step forward, I just want to quickly talk about two major classes of reactions. We have exothermic and endothermic reactions. An exothermic reaction is going to release energy. All release. So an exothermic reaction will heat up the surrounding environment as it progresses, whereas an endothermic reaction requires energy. It will cool down the surrounding environment when it progresses forward. We graph these out on graphs that have, we measure energy on the y-axis and time on the x-axis. Two classic exo and endothermic reactions are cellular respiration and photosynthesis. We're going to be talking in much greater detail about these two reactions later on in the year. But just to give you a sense of what's happening in each of them, they actually both have the same chemical formula, but kind of palindromic or inverse of one another. So they both start out with glucose, C6, H12, O6. I guess they don't both start out. Cellular respiration starts out with glucose and oxygen. I'm going to give you here the unbalanced chemical equation for cellular respiration. And glucose is broken down. The energy stored within this molecule is released, and the oxygen is consumed. And on the other side, we get CO2, H2O, and energy is released. Now, if we look at photosynthesis, we can actually take the products of our cellular respiration reaction and copy over the same arrow, and the products here are the reactants here. So these two processes are linked to one another. Cellular respiration is the breakdown of glucose into carbon dioxide, water, and releases energy. And photosynthesis is the fixing of carbon into glucose. And in the process, water is consumed, energy from the sun is required, so solar energy. And the outputs are glucose and oxygen. Okay, so if we were to diagram these two reactions out on a graph, we'd see it looks something like this. We have our reactants here, and if we were to plot out their energy level, it would be somewhere up here on our graph. So we start out at a certain energy level, and then if we were to measure the energy of the products, we would see that it's somewhere down here on our graph. So the difference between the initial energy and the final energy is called delta H, and in this case, it's going to be negative. So energy is released in this process. But the way that this reaction progresses forward through time, it's not just a linear straight line like this. In order to turn or to harvest the energy from glucose and get out the energy and lead to our products, we actually have to put in a little bit of energy to get the system going. Imagine this glucose here is wrapped up in a log. So a log is just a bunch of glucose monomers all strung together to form this polymer called cellulose. And then, oh, Zach's coming in. Zach, what's up? I'm recording your screencast right now.
I can't take the test.
You can't take the test?
Open for me.
Oh, it's not open for you. Give me 1 second and I'll open it up.
Okay.
Okay.
Thank you.
Okay, I'm going to pause this. Okay, sorry about that. We're back at it. I kind of forget where I was, but I think I was talking about activation energy. Okay, so we have a piece of wood. It's not just going to spontaneously combust. We have to provide a little bit of energy input. So we have to light a match, for example, in order to get it to start to burn. And that's called the activation energy. So the curve of the reaction looks something like this. We have to actually increase the energy before we can release it and burn our log. And this distance between the initial energy of the reactants and the energy we need to provide to get the reaction started is called the activation energy, but I'm going to put it here. And again, it's the measurement from here to here. It's this whole distance. So this is our activation energy. And the same thing would be true of, if we copy this, our exothermic reaction here. So if here's our energy of our reactants, and here's our energy of our products, we actually have to provide more energy for this reaction to take place. And again, this distance here from the initial energy is called delta H, and in this case, it's going to be positive because it's an endothermic reaction, so we required energy, so our products have more energy than the reactants, and the difference between the peak of the reaction and here is our activation energy. Okay, so what does this all have to do with enzymes? Well, I just told you above that enzymes speed up the rate of reactions by lowering the activation energy. So I'm going to show you what that looks like in terms of the graph. If our black here, our black reaction curve is, the rate of, what's going on with my pencil? It's not screwed in. The rate of reaction without enzyme. My blue curve is my rate of reaction with, with the enzyme. Okay, and I'll show that here on the graph. So with my enzyme, my reaction is going to look something like this. And something like this. So you can see here in my blue curve that I actually get product faster than I would without the enzyme because I have a lower overall activation energy with the enzyme compared to without the enzyme. And so enzymes don't change the overall amount of energy inputs or outputs of any reaction. They just lower the activation energy and they speed up reactions by lowering the activation energy in such a way that they can make life possible, because they make reactions that would take a really long time happen really quickly. And they do this by orienting their substrates or their reactants in a very specific shape by their folding patterns. More on that later. Okay, This turned out to be slightly a longer screencast than I intended, but I hope you liked it. See you all in class tomorrow.